I'll try to post this. Okay, so we're on page 3. Okay, and this is solution. Preparation methods and acid-base titrations. Okay. Most journals people will put an objective of this section. Well, this is a methods development. Solution preparations. Like that. And then an analytical method. Acid-base titrations. Okay, and it just kind of reminds you generally what you're doing. So what I've got to teach you now is how to make a solution. Okay, so down here, part 1, solution preparations. Like this. We have 3 issues that we have to do. Solutions from MFG, manufactured solid stock. Okay, so that's one source that you have to start with. Okay, they may send you a big can, they may send you a jar or a bottle or whatever. Solutions from liquid concentrate. Manufactured liquid concentrates or liquid stocks. Okay? And you may not want to work all the time with a manufactured liquid stock of, say, sulfuric acid. It's 95% active. Or nitric acid or sulfuric acid. Those are 36-37% active on the average. They run about 12 molar. Well, that's nasty stuff, you know? And you'll learn about that because you should go home and look up the chemicals we could talk about today and MSD sheets and stuff like that. But you will dilute, you'll take some of that acid and you'll put it in a quantity of water, add some more water to it, and you'll put it in a bottle, mark it's more dilute than the stock you got from the manufacturer, but it's not as hazardous to work with. And you take a portion and dilute it and make whatever you need for your laboratory. So this is called the dilution process. Dilution of lab stocks. Okay? Okay, as you look at this handout, notice it's got preparation solution from solid stock. It's got a little blurb there. Preparation solution from liquid stock. Here's a blurb here, right here. And the dilution equation kind of runs off my page a little bit. I'll scoot that up right here. So this is what I'm about to cover. And this is what I want you to know. Very important as you move forward in your career in chemistry or whatever. You need to know how to make a solution. What I want to do now is I'm going to tell you about solutions. This is just a little short lecture on the nature of solutions and diluting solutions and so forth, so you can have an understanding of the technology that you're fixing to work with. Call it solution tech. If we need to make a solution by definition is a homogeneous mixture. Now you can make solutions out of liquids and dissolved into solids, and solids back dissolved back into liquids, and states of matter mixed together in a homogeneous concept is a solution. Now we will be working primarily with liquid and solid into liquid solutions in the work we're doing. Okay. A solution consists of two parts. Simple solutions. There are complex solutions which have more than two parts. But right now you're going to work with two parts. That is A, the solvent, and B, the solute. Please note that a solution equals solvent plus solute. Okay? So if you wanted to know, you've got 100 grams of solution, some of the weight of that 100 grams is going to be solute and some of it's going to be solvent. All right? Now, the method of making solutions by definition is dissolve solute into sufficient amount of solvent to give desired total volume. That last word says volume, believe it or not. Okay, we're going to prep a solution here. We're going to dissolve solute into a sufficient amount of solvent to give a desired total volume. So I've said, okay, you're going to dissolve 20 grams of reagent X to make 250 milliliters total volume. Now listen to what I'm telling you when I give you this explanation. What I'm telling you to do is, in a mixing container, say a graduated cylinder, whatever, you're going to take 20 grams of X and you're going to put it into the cylinder. Then add solvent up to, but not to exceed, 250 milliliters. So you'll start out with your solid, and then you'll bring it up. Start out with your solid, and then you'll add your solvent, and it'll be up to here to 250 milliliters. And stop. What I didn't say is put in 20 grams and 250 milliliters of solvent. You hear that? I did not say put 20 grams of X and then throw in 250 milliliters of solvent, because the solution itself consists of two parts, and part of the space in that solution is taken up by the solute. So if you put 250 milliliters of solvent in there, it's going to be too dilute. It's going to have too much. Now, this is an understandable point of issue, but I want to be sure you understand it so that as we go forward, you approach it knowing that when you decide on how much reagent to put in here, the next step is up to but not to exceed the solution total volume. It didn't say add solvent 250 mils. Okay, it's a very important point in techniques for making solutions. Okay. Next one. Okay. This is all going to be, I'm going to publish this, hang in there, okay. Draw a couple of diagrams. Here's a beaker, and beaker number, same beaker after you add some more solvent. Okay, right here. So here's the top of our solution, and so we have, no, take that back. Here's the top of your solution right here. Say you've got 20 grams of X in there. Okay. Then I'm going to add solvent up to this point. Case 1, case 2. Okay? And so we've now we've got a solution, case 2, that still's got X in it. Now stop writing and listen to the question I'm going to ask you here. And it's obvious. I think everybody can manage. I put 20 grams over here, and all I did was add solvent up to that point. How many grams of X do I have over here? How many? 20. 20, same amount. Did everybody understand what happened? Really? I didn't change the mass of, I changed the volume, I changed the concentration, but the mass of X didn't change. I put 20 over here, and then I just poured some solvent on top of it and diluted it. Yes? Yep. So I still have 20 grams of X over here. Now, when working with solutions in chemistry, what do we work with? We work with concentration terms. A concentration term is an amount of solute. What's the solute? It's a small amount. It's a smaller component. In an amount of solution. It's not in an amount of solvent, it's in an amount of solution consisting of 2 parts solute and solvent. There are many ways to represent this. Grams per milliliter, pounds per gallon, grams per liter, and many ways to present it. But in general chemistry 2 and 1, our most dominant unit that we use, anybody know? Molarity. Has everybody heard of that? If you haven't, now's the time to listen, because this is used more than anything else. Molar solution. And it's called molarity. And it's a capital M by symbology. In using molar, we use moles. Is a mole and a molarity the same? No. A mole is a mass. Stop right, just listen to it. Moles is a mass term. Molarity is a concentration term, like density. It contains a distribution of solute and solvent in solution. A mole is the mass, gram, pound, whatever. A mole is the mass, weight, of reagent containing 6.02 times 10 to the 23rd particles of that reagent, or 1 Avogadro's number. And will represent one formula weight, always. So if I'm talking about 1 mole of hydrogen, it's 1 gram for the atom. 1 mole of molecular hydrogen, H2, would be 2 grams. Okay, 1 mole of water is the formula weight of water. Grams, 16 plus 2, 18 grams, right? That's 1 mole of water. Sodium chloride, salt, table salt. That's 58 grams is the formula weight. 35 plus 23. Sodium, 23, 35 for chlorine, right? Add them together, what do you get? You get the formula weight. So if I take 35 grams, there's 35 grams of sodium chloride. That's got 6.02 times 10 to the 23rd molecules of sodium chloride. Okay, that's 1 mole. In solution preparations, it is moles that we dissolve into the solvent. A mole is equal to a mass in grams of the reagent divided by the formula weight of reagent. And I'm not saying you should have come to this class knowing this, but yeah, you should have. But considering the fact that we had a big break, I'm going to go back over. Okay. Mass, say for water, H2O, formula weight is 16 plus 2, that's 18 grams, and we say per mole, or 1 mole weighs 18 grams. So if I took 18 grams of H2O and I put it into an solvent, the solvent's alcohol. Water's in isopropyl alcohol, infinitely soluble. So I've got a solvent over here, and I put 18 grams of this water into 1 liter of solvent. We just call it solvent. What have I done? I put 1 mole of H2O into the solvent. That's 1 liter. And the final volume, 1 liter final volume. What this gives me is a 1 molar solution. That's what I have. I take moles. Now I still have 18 grams because 18 grams is still 1 mole. But we call it 1 mole or 1 molar. Molarity is a density number. Okay, now watch what happens. Now, this is case 1. Now case 2, if I took 9 grams of H2O and put it in that alcohol, I have 9. How does 9 compare to 18? Half, isn't it? It's half molar now. You see? Yes. Okay, so 9, that's 9 out of 18, or 1/2 mole goes into my mixing beaker. So of solvent. So I have 1/2 mole in here, and this is going to give me a 1/2 molar, usually represented 0.050 molar. So if I can convert the mass I put in there to moles, then I can take that and dissolve it up to liters, and that's the molarity. Dissolve it up to 1 liter. What is molarity of 25 grams of NaBr, sodium bromide, in 250 milliliters of solution? Okay, there's your problem. 1, 25 grams sodium bromide goes into the beaker. 2, add water up to, but not to exceed, 250 milliliters. So now you have 25 grams of sodium bromide in that solution dissolved. Right here. Yes? Oh, sorry. Molarity of solution is moles of solute. So the biggest issue now is, how do I take that 25 grams right there and convert it into moles? Divide by formula weight. Grams to moles is divided by formula weight. Grams to moles is divided by formula weight. What did I say? Grams to moles is divided by formula weight. Anybody in here not know how to calculate formula weight given a formula? If you not, let me know. Okay, so we have 25 grams of sodium bromide. Okay? From the periodic table, we're going to get the formula weight, because moles is equal to, listen to me, grams given divided by formula weight of the reagent or the molecule that you're using. And so that will be the moles in 250 milliliters. So I have 25 grams. Now I need the formula weight of sodium bromide. Well, looking on the periodic chart, I see sodium over here is 23. If you can't see that, that's all right. I can't see it either, and I'm closer than you are. Okay, 23 and bromide's 80. So 23 plus 80 is what? I don't know. We'll add it up. Okay. 23 and 80, 103 grams per mole. Everybody good? 103 grams per mole. 103 grams. Okay. So now I need to divide by 103 grams per mole. Grams over formula weight. is moles. Grams over formula weight is moles. It's not molarity now. Molarity is moles over liters. Everybody keep? Okay, so I want you to work on that this weekend. Moles is mass over formula weight. Mass over formula weight. But molarity is moles over volume in liters. Okay, so moving on. This gives us 25 over 103. Now we start using the calculators. I ought to get glasses. I'm tripping over myself. Well, that's dead. Okay, so we have 25 grams. I'm going to enter 25 in the calculator divided by 103 equals 0.243. I'm moving it. 0.243 mole of sodium bromide in my beaker up here. That 25 grams is now 0.243 mole dissolved in 250 milliliters. Now the molarity M of that solution is moles, which is this number, divided by the volume expressed in liters, okay, and we get a number. And so moles is 0.243 moles of sodium bromide. And what did I say was the volume? 250 mils, convert to liters, divide by what? 1,000. And so I want to divide by liters, 0.250 liters. See that I did? Everybody still with me? Moles per liter. Moles per liter is moles. Molarity, excuse me. So that divided by 0.25 equals 0.97, 0.97 molar solution in a BR. And we typically tag it with an AQ to indicate that the solvent is water on the end, down like that. So when we work with solutions, for the most part, we're going to be working with molarity. But what you have to understand is the majority of the problems are going to ask you, say, well, 15 grams was dissolved in so much volume in milliliters, and in your brain you start to say, well, I got to convert all that to molarity. Moles, divide that mass by formula weight, divided by the volume expressed in liters, and you get the molar concentration. And as I get deeper into this today, I got one more hour to give you, and I'm going to slam it to you. So hang in, tighten up your belts, and use your shoulder harnesses if you have to. Say you're given 65 grams of sodium nitrate, okay, and 726 milliliters of solution. Calculate Ca, that says Ca, calculate the molarity of the solution of sodium nitrate. Okay? Well, I've given grams and I've given milliliters, and so I need to get, if I'm going to get molarity of this, molarity is equal to moles of the sodium nitrate in a volume expressed in liters. So I've got to make those conversions to be sure I have the right terminology and the right numbers. Okay, how do I get moles from grams? Divide by what? Formula weight. Divide by formula weight. Everybody still with me? Moles is grams over formula weight. Well, let's get the formula weight of sodium nitrate. Well, I got a sodium and a nitrogen, and I got 3 oxygens here. Okay, sodium is 23, nitrogen's 14, and oxygen's 16. And so when it all said and done, it's going to be listed as grams per mole. Okay, so that's 23 plus 14, 48. 8, 9, 11, 12, 13, 14, 15, 4, 5, 6, 7, 8, 85. Y'all get it? Okay. 85 grams per mole. Okay, that's the formula weight. But I only have 65 grams in that solution. And I have to express it in moles. So I'm going to watch me what I do here. Moles of sodium nitrate be 65 over 85 parenthesis moles of sodium nitrate. And you'll do that on a test. When you get there, you'll have to make that conversions like that from all this. And I found it very nice. That's mass given over the formula weight. And I just kind of squeeze that in there over a big line. Now, the volume, I just simply divide by 1,000. That's moving the decimal 3 places to the left. So I'm simply going to come in here with 0.726 liters. See how simple that is? So you got a mass, you got a volume, and you take your formula weight, divide into your mass, put it in parentheses over the line, that's your moles, divided by the volume, expressed in liters, and it automatically kind of gives it to you very quickly. And that's going to have to be done quickly and efficiently in some of the more complex problems that we're going to go to in a minute. So we're looking at 65 divided by 85. So we're at, I'm going to spread this out, that's 0.765 mole of the sodium nitrate, 0.726 liters, divided by 0.726 liters. And I got a 1.05 molar sodium nitrate solution. So now can you take mass, dissolve it in the solution, and given the volume, and figure the molarity. Make up your own solutions when you get home. Send me a note and I'll make up some for you if you don't want to use your brain. Okay. Solution prep from solid stock. And of course this refers to the manufacturer's solid stock. So you go to the stock room, you pull potassium nitrate off of the potassium permanganate or whatever you're trying to make a solution of. And you scrape out some into water and you dissolve. And that mechanically is how you make a solution. But you need to use the proper amounts. So typically you'll get a problem like this. Prep 500 milliliters of 0.75 molar, let's make it 2.75 molar sodium hydroxide aqueous solution, like that. It's really easy to make this, because if you look at that handout I gave you, I give you a formula down there that if you have a solid stock, use this formula and you can get the mass that you need to put in the solvent. So if you look, you'll see this little right here in your notes. Mass of solid stock needed to make the solution you want. And here's a little formula over here. M stands for the molarity you want. Volume is the V, formula weight of the solute, and the purity factor. Because when you get a reagent from a manufacturer, it'll have an assay label on the side of the bottle, and it'll say purity on it. Typically, sodium hydroxide, being a hygroscopic, meaning absorbs water, comes about 98% active. And we express that purity factor as a decimal fraction. All right, so the question is, it says prep 500 milliliters of 0.25 sodium hydroxide. The question is, with it intuitively, and you're not having this, and I'm not going to put that in here. It says, how many grams sodium hydroxide do you need to dissolve into a solution total 750 milliliters? Well, the formula is molarity times volume expressed in liters times the formula weight of the NaOH over the purity factor. What is it? Well, the molarity we're looking for is 2.75 molar. So I'm going to write that 2.75 molar. Actually, that's moles per liter, but I'm just going to put a big M right there. Okay? The volume you need is 500 milliliters, and it needs to be expressed in liters. So that's 0.500 liters. And the formula weight of sodium hydroxide is 23, 16, and 1. 23, 33, 34. 23, 16, and 1, 6, 7, 8, 9, 10. I thought it was 50, yeah. 50 grams per mole for the formula weight. And again, the purity factor in this stock manufactured is about 98%. And what we do is we put a decimal fraction down here in the denominator. It has no units to it. Now, when everything's said and done here, this M right here, watch what I do. This M right here is actually moles per liter. So moles will drop out, liters will drop out, and you're left with grams. Magic. Okay, 40. All right. So in everything said and done, this is just simply going to come out in grams. Is when it finishes. Molarity times volume times formula weight over purity factor. That's an easy formula. If you look at the next one, when you do liquids, same formula, except you have to divide by density of this liquid stock. And this only assay label too. Okay, so we need 56.12 grams of sodium hydroxide. Okay, now what are you going to do with this? You're going to go to the bottle that you have. You're going to pull out 56.12 grams sodium hydroxide solid. You're going to transfer that into your beaker, and then you're going to add solvent up to, but not to exceed, 500 mils. Solvent up to, but not to exceed 500 milliliters total. And then you'll transfer it to a stock bottle, put a label on it, date you made the solution, tell it, stick it on the shelf. Okay? And that's it for making from solid stock. Next, we want to look at, okay, so we're going to now, the second part of our handout, you'll see here it has a formula just like what we did right here. And your interest is to have a problem and use this formula this time. Okay? Typically, these will be acids. Now, ammonium hydroxide and stuff like that comes in liquid form, so that's one of the few bases that is worked with. But the majority of these are acids. So what we're going to do is we're going to dilute a stock acid solution. Okay, so your job or your project is prep 250 milliliters of, let's make 3 molar, 3.5 molar HCl aqueous from liquid manufacturer stock that has specific gravity of 1.18, which is the same as density because the solvent's water, grams per milliliter. How much of the HCl do you need to extract from that bottle? So you'll be given this kind of problem, but intuitively you want to ask yourself, what volume of liquid HCl stock do I need? It's what you're in essence asking yourself when you make a solution from a liquid stock. Okay, fine. Okay, so what you have is this bottle over here, liquid bottle, and on the outside it'll say 37% HCl. That means there's 30% by weight, 37% by weight in HCl. It'll burn a hole in you if you get it on you. It'll make holes in your blue jeans if you get it on you. So you want to protect yourself, blah, blah, blah. Read the MSD sheets before you start extracting. Okay? So the question is, what volume? Well, if you look at the formula that I published on that little handout, it's the volume in milliliters that you'll need to extract, and you use a pipette to pull it out and transfer it into the water sample. Okay, now you'll have to start by always adding a strong acid into water. You never dump water on top of strong acid because it explodes. See, remember A&W root beer? Have you ever heard of that before? Yeah, some of you have. Add acid into a small sample of water, at least twice the amount of acid volume. At least twice. And then finish up to, but not to exceed the volume. See the point? Molarity times volume in liters times formula weight of the acid divided by the purity factor, that'll be the 0.37, and the specific gravity in grams per mil. Because we're working with a reagent that's dissolved in water. Specific gravity in anything else, you'd have to have a different number, but in different consideration. But in the work we're doing in this course, it'll always, specific gravity will always be in grams per mil because the solvent's going to be water, I promise you. Okay, so we want to make a 3.5 molar solution, okay? And we need 250 mils of it in liters, divided by 1,000, so I move the decimal over 3 places, like that. The formula weight of hydrochloric acid is, am I not turned on yet? I am. 36 grams per mole, and then we want to divide by the purity factor. It comes to you 37% from the manufacturer, so that'll be a 0.37 factor, right there. And then the specific gravity is 1.18 grams per milliliter. That's mole, not milliliters. M-O-L, right there. And when all's said and done, this thing's going to give you how much you need to extract and dissolve up to, but not to exceed 250 mils. When this thing is said and done. So it's 3.5 times 0.25 times 36 equals, divided by 0.37 equals, divided by 1.18 equals 72.15. 72.15 milliliters of stock HCl, 37%, dissolved into 250 milliliter solution. In other words, you'll dissolve it up to, but not to exceed the 250 mils. Note, caution, add stock concentrate into a quantity of water solvent less than total volume of solution needed, then add solvent up to, but not to exceed, desired volume, total volume. I can't emphasize that red notation any more than that. So we know we're going to need to extract 72.5 milliliters. So I'm going to probably, and I need 250 total. I'll probably get a beaker and put about 100 or so mils or better of water, solid. Then pipette with an appropriate pipette. Of course, you have goggles, you've got your apron on, gloves, and the necessary protective gear. And transfer 72. And you know, if you don't have a pipette that'll pipette 72.15 milliliters, get you a dry reservoir or sample, big test tube or something, and transfer it in portions until you get your 75.15 milliliters of acid. And then you slowly, with stirring, stir bar in your own plate, slowly add that acid in that water. Once it's dissolved, then you can continue to bring it up to what is specified in the instructions without killing yourself. If you try to pour water onto 72.15 milliliters of 37% HCl, it'll blow up your face. And I kid you not, it will take your face off. When I first started, consider here, one kid put the acid in first and poured the water on it. And I was too dumb to get off an escalator and power failure, but and I didn't tell him about it. And it didn't hurt her, but it blew out and had a big old spot on the ceiling. I swear to God. And had she been looking down in it, she'd have ate that. Please take that to heart. Thank you. Of making solutions. Third method of making solutions. And this is the dilution process. The dilution equation. The dilution equation is used for just what it's saying it is. To take a concentrate and dilute it to a lower concentration. The dilution equation used to determine the volume, typically in milliliters or liters, volume of concentrate needed to prep a more dilute sample. Let's say you are given that 3.5 molar lab stock HCl aqueous solution. Probably something like that. Here's what you're given. And you'll have instructions prep 100, let's say 150 mils. Yeah, keep it kind of mixy. 150 milliliters of 0.25 molar HCl aqueous solution. Okay? Now, what you have to understand about this, the dilution equation comes from the definition of molarity. The dilution equation comes from the definition of molarity. What was molarity? Did I say moles over liters, right? Moles of solute divided by volume of solution expressed in liters. That's a simple equation. It's a density equation. Moles is the mass over volume. Solve that equation for moles. So I multiply both sides by volume. So moles now is equal to molarity times volume expressed in liters. That came right out of the definition of molarity. Okay? When I make a solution, I'm going to pull out so much of the concentrate and I'm going to add solvent up to here to dilute it, right? So I have in here moles of HCl. That says moles of HCl. Let me clarify. Moles is a mass number. It's 36 grams, say for 1 mole. You'd use fewer moles, but regardless, it's moles. It's a mass number. It's like pounds. When I pour the water on top of it, do I still have the same number of moles in the beaker number 2? Now listen to what I'm saying. For God's sake, listen to me. Do I still have the same number of moles in beaker number 2? Yes. Yes. So moles over here in 1 are the same number in 1 and 2 are equal. Still with me? So if this definition right here is moles, then I can say molarity times volume of the concentrate side is equal to molarity times volume of the diluted side. As you mentally put together your problem like this at the top here, what you're trying to determine is this number. How much of the concentrate do I need to pull out that I got on the shelf? I know what the concentrate is. It's 3.5. And this is what you are going to make. This is the solution you're going to make. So you have all the numbers except that. We have on the shelf for the concentrate 3.5 molar solution. We don't know what we need to extract from the concentrate. But we do know what we want to make. We want to make 150 milliliters of 0.25 molar HCl. So I want 0.25 molar. This is what we're going to make. And I'll go ahead and use liters for this one. 0.150 liters. Now you'll learn that since both sides are the same, I could have left this in milliliters. We'll keep it in liters, keep confusing everybody. So the amount of concentrate I will extract, put in the mixing vat, dilute up to 150 mils, is calculated now. So the volume of concentrate needed, that says needed, is equal to 0.25 molar times 0.150 liters divided by 3.5 molar. Molars drop out, and this will give me so I need to extract 0.0107 liters of lab stock concentrate. Multiply that by 1,000, which is 10.7 milliliters of lab stock concentrate. Transfer to mixing container and add solvent up to, but not to exceed 150 mils. This method is way more accurate than the first two. Now you get pretty accurate in the first two. Don't misunderstand me. But if you make a lab stock, and it's easy to pipe that 10.7 milliliters of that concentrate, and then transfer it, and then add your solution. There's all kinds of mixing reservoirs. You have volumetric flasks, you have calibrated beakers, you have all sorts of accuracy and precision devices, so that you can make solutions that are very accurate. And no matter how hard you try, you can't prepare exactly what you think you're trying to prepare. You get close, but you can't. So what do? You verify. You have to verify this one. Okay, so you've prepared 150 milliliters, 0.25 molar, you think, of HCl. Are you sure that you made a 0.25 molar solution? You're going to be close. That's a fact. But you now need to be able to verify that. And the way you do that is with acid-base titration. And that's the last part of this, and I can get through it. In a terminology context, the titration of your prep is called calibration of that prep. In other words, you're verifying what the exact concentration is, so that when you do further research, you know what you have. You're close, and you may be dead on it, but you can't depend on that until you titrate. Okay? Now, what you're doing is you're going to be adding an acid of known concentration into the prep, the base prep of unknown. You do know it's close to 0.25, okay? I know that. But we're going to call it an unknown because you're trying to verify it. We'll give a salt plus water. Okay? So you have a reaction going on here where you have an acid reacting with a base, producing a salt and water in a 1-to-1 reaction ratio. So the calibration that you're fixing to use is, as a matter of fact, 1 mole of acid plus 1 mole of base will give you a complete reaction. It'll completely react out all of the base if you put equivalent amounts in. That's why it's called its equivalent point. Okay. The reaction you're going to use I'm going to put this over here first, NaOH, aqueous, right there, is potassium hydrogen phthalate. It is a universal titrant acid. It is 100% pure and is not corrupted or anything, and is used widely all over the world. It's called KHP little h, and it's aqueous solution. It comes as a crystalline solid. I'll show you Monday, okay? On Tuesday when we do this. So this is a 1 mole to 1 mole ratio to produce sodium, sodium, potassium, phthalate. The hydrogen is transferred over Bronsted, and we'll learn about that later, and produces water like that. So there's your mechanism. You're taking KH and the H out of this compound. It's transferring over here. It's called potassium, hydrogen, phthalate. Now, okay, so this is going to be a titration, verify. So what we're going to do is we're going to set up a titration system, and I will have all this Tuesday. right here, and what you're going to do is you're going to put about 25 milliliters of your base solution and down here. And up here, you want to put in your KHPH solution. Now, when reacting on a 1-to-1 reaction ratio and using a titration method, if you use one equal concentrations of acid and base, listen to me, stop writing. If you have equal concentrations, it'll be very, very difficult to titrate. What you want to do is use half concentration. Now, this is a rule of thumb to make life tolerable. You want to use half concentration as you have, you can calibrate. In other words, what is our estimated concentration here, guys? What did we try to make up there? What was the concentration we tried to make? Point what? Come on, guys. I ain't got time to play with you. 0.25. Somebody bark it out. 0.25. So what's half of 0.25? About 0.12, right? Why not just make a 1? 0.1. Okay, see what I'm saying? The reason is when you titrate, you're going to start here with your base. Well, actually, this is going to be backwards. You're going to start up here with your base. And it's going to be around 12 pH. And then you're going to start adding that acid. It's going to start neutralizing, and then it's going to get close to neutralizing all of the acid in your beaker. And if you go too fast, if it's too concentrated, it'll drop down through the equivalence point faster than you can control it. And you won't get accurate results. So that's why I tell you, let's use a 0.10 molar KHPH solution so that we can get more points in here. And we can determine what our equivalence point is a whole hell of a lot easier, with a lot more accuracy, and you look good doing what you're supposed to be doing. That's what you paid your money to learn, how to do things accurate. So we're going to use this. So we've got this set up. So I need to prep my KHPH solution. Okay, prep. We got 50 milligrams. Prep 100 milliliters of 0.10 molar KHPH aqueous solution. It's solid. Formula weight's 204. We can drop it in. Solid. Formula weight equals 204 grams per mole. Comes as a pure 100%. Purity factor is 100%. And so what do? Okay, you get the jar from the manufacturer, and you figure grams of KHPH needed is equal to molarity times volume times formula weight of the KPH over purity factor. Well, let's see, I need 100 mils, molarity 0.1, 0.1. I need 100 mils, 0.10 liter. Formula weight's 204. Purity factor's 1.00. And all that's going to come out in grams of KHPH that you put into a beaker and dissolve up to, but not to exceed 100 mils. I got a 100 milliliter volumetric dilution device that you can use and make a very, very accurate prep here. .04 grams. Now that's easy to measure out, okay? And you can count on that to be your 0.1 molar. Now, you don't have to spend all day getting 2.04. I'll tell you what. This is theoretical, right here. Actual, let's say you go to the balance and you scrape off the best you can, grams of KHPH is now equal to 2.111 grams. Now you don't want to sit there all day and scrape that stuff back in the beaker, but when you make a prep with that 2.111 grams, it's an accurate prep. If you dissolve 2.111 grams of KHPH into 100 milliliters of solvent, what's the molarity? Well, molarity is moles over liters, right? So molarity equals moles over volume in liters. So 2.111 grams of KHPH. How do I get grams to moles? Divided by what? Formula weight. Thank you. So 2.111 divided by 204 moles divided by a volume of, I'm going to make 100, so that's a 0.100 liter. And so when you dissolve, you get close. You do your calculation to determine how much you need, but you don't beat yourself up trying to get that number. You get close to it so you don't use up the whole bottle. So you got 2.111 divided by 204 is equal to that, divided by 0.1 equal. So you've made a 0.1034 molar KHPH aqueous solution. That's the standard. So we have now 100 milliliters of KHPH that we're going to use to calibrate 25 milliliters unknown molarity NaOH. And so we bring it up to 50, well it's 0 actually. It's a 0 point here and it'll have a marker down here at 50 mils. Okay? And since it's a 2 to 1, why don't we do 20 mils right there? Because you'll hit your equivalence point at twice that if it's that close. 20 mils of 0.25, we know it's around 0.25. Okay? This is 0.1. Okay? So how much of the KHPH? Well, you'll use almost 50 mils of it. So you won't have to, if you go to the 50, you add some more and keep up with it to reach your end point. Okay, so here we have our sodium hydroxide down here. My red pen. So there's our KHPH. Here we've got in here 0.1034 molar KHPH here, and we have 20 milliliters of unknown molarity sodium hydroxide down here. Okay, when I drop one of those red dots into the blue dots, it's going to react with the blue dot. It's going to be KHPH plus the NaOH. It's going to give me the sodium potassium phthalate plus H2O. And this is a salt. And that's going to be the black dot when I finish with this. Your base is the blue dot. And I lost my red acid. Here it is. Is a red dot. Okay, so I'm now about to start dropping my preparation into that solution. So I go ahead and I put one of them in. Right there. Okay. It's going to turn one of these into a black dot. You still got a more basic solution. So what you're going to see as you go along is you're going to start here and it's going to go along here. That's your first dot. It's going to come down just a little bit because we've added some acid. Okay, we come in here and we add the next one in. Okay, so we added the next one in, so now here, and so our dot's going to go to about right there. So it's going to come down in pH as we're reading it. Because this is the data. It don't look anything like this, but you've got to think of this in terms of the reaction you're running up here. That's what chemists do. Okay? Now, it keeps going, and you'll add another one. It knocks that one out. And so it about halfway. Now, this is called the halfway point. Okay, then you put in another one. It'll neutralize another one. It's getting closer to more acidic, and it's going to start getting over here on the shoulder. It's going to start coming down a little faster. And then you put in another one. You keep going, and it's going to start coming down this shelf right there. Then you're going to put in one more. Now you'll have some extra left up in the burette in there, but it's going to take out that last one, and you're going to be right here, and that is called the equivalence point. Do you have any acid in the beaker? Do you have any base in the beaker? No. All you've got in that beaker is salt. That's the only thing there, because you've neutralized everything that was down there. And that pH is going to equal 7 using this system. That's your equivalence point. So you're trying to find that equivalence point, because that equivalence point, if you find it exactly, will allow you to determine the concentration, because the moles of acid used equals the moles of base neutralized, because it's a 1-to-1 reaction ratio. Okay? And then if you added these other two in here, it would just be excess acid in here, there, and say right there, and it would just go on out like that, and you would have a titration curve that would look like that. All right? And when you find the equivalence point, come down here, and this is the VEQ. It's called the equivalence volume. All right, now what's so good about the equivalence volume? That equivalence volume is the volume of acid you added. So let's say we're close to 0.25. We've got 20 mils in there. Let me do a, okay. Say we added all of the KHPH in here, and we hit the equivalence point at 50 mils. Okay? You know the concentration of the acid. You know how much acid you used. What's the mole? How many moles of acid did you put in the thing? Well, molarity times volume equals moles. Molarity is 0.1034 molar times 0.05. I changed milliliters to liters. 050 liters. God. I get to swinging around here, and there we go. That's close enough for right now. Okay. We've got 0.0052 mole of KHPH that we used out of the burette. How much acid did we neutralize? Same amount, because it's a 1-to-1 reaction ratio, right? 1-to-1 reaction ratio. If we've got this many moles in 20 mils, what's the molarity of what our solution is? We got that much over 20 mils. So it's moles over volume in liters. So now we can finish our little calibration. Molarity of actual, molarity of NaOH prep is equal to what we neutralize. Well, we know we have 0.0052 mole of KHPH in 20 mils and 0.020 liters. And so this very neatly .125 molar. You thought you prepped a 0.25. Sorry about that. Now the volume of KHPH added was, I just chose it, okay? Now it's really going to come out close to your 0.25 when you finish with it. It really will. Okay? And it'll probably take more than 50 mils if you did that one anyway. But that's the objective here of you being a decent chemist. You've got to understand the concept of solutions, how to make them, how to use them in a titration, and how to come up with how much you're going to use. And you have seen there are some others coming in the future. If you understand this, it'll make my life a lot easier than it is right now. Now people study this stuff with all due diligence because we're going to be using this concept and these ideas from now to the end of the semester. Now we'll beat you up with them. Okay, and they're definitely an important concept. And that's why I spend so much time on it, trying to teach you the fundamentals of solution prep, what it means, and how to apply the concepts to reactions and kind of an experimental concept. Yes, sir.
That should be 0.26.
Okay, let it be 0.26. If you're going to use the, I'm going so fast, man. I'm surprised I got that far. Thank you for the day. Oh, this will be part of your quiz online. I do have several lectures planned online for both Chem 1 and Chem 2 on these subjects. Solution preps and titration analysis and whatever. There's several lectures. If I'm still alive, I'll see y'all too. Wasn't that fun?
Yeah.
I'm telling you, I knew I could.
It was a lot.
It's a lot. You're getting it a lot.
Okay, so is all of this supposed to be in our lab notebook?
As much as you think you need,
Okay.
so that you can look it up 5 years from now
Okay.
and teach it.
And the other titration sheet, can we glue that in our notebook?
Yeah.
Okay.
Whatever you need to help you get through the experiment is what you use. I'm good with it.
Okay, so we
As
can put
long
whatever
as-
we want.
I'm sorry?
We can put whatever we need.
As long as it's organized.
Okay.
In the syllabus, and I think there's some other stuff on there, it says, use this organization.
Okay.
Title, purpose, put all your background, put all your data, and, you know, keep
Okay.
that, so I can find it, that's real.
Okay.
And, you'll make an A.
Hopefully. Thank you.
You do what I say, you get an A.
Yeah.
You'll post this tonight, right?
Huh?
You'll post this.
I will post it.
Okay.
Now, there are some more of these online. If you know you how to get into my lectures.
Yes.
Okay? Look at the titles.
Okay.
I think I've got a couple in Chem 1 toward the end of the semester.
Mhm.
A couple of lectures on this.
Yes.
And under exam 2 in Chem 2. There's,
Okay.
there's 2 or 3 of these. I'll throw this one up there tonight.
Okay, thank you.
Okay, sir. Y'all have a good weekend.
Thank you.
Okay. I'm going to take a shower and
Do
take a
you
nap.
have dates for our exams?
Yeah.
You do?
Actually, when I finish 13, when we get through this, we'll be through with kinetics.
Okay.
And I'll have you kind of primed and prepped we'll do Monday, we'll do the titration experiments, preps, and kinetics.
Okay.
Okay, all that's be in one day. Then Thursday next will be equilibrium. It'll take me 2 and then an experiment's so easiest.
Uh-huh.
1, 2, probably 2 more weeks and then an exam.
Okay.
Somewhere
All
in
right.
there. Yo.
Thank you.
All right, thank you.
Yes, sir. Hope you
Have a
learn
good
something.
weekend.
Send you an email if I have a question.
That's right.
Thank you very much.
You got my address.